Hey Vsauce, Claire here. And here, near Earth's surface, objects experience a gravitational acceleration of around 9.81 meters per second squared. Our mass, black hole, has a gravitational acceleration 1.6 trillion times that. This means that these gravitational pulls are so strong that not even light can escape them. Fortunately, for humans, Earth, and the solar system, we don't experience gravitational pulls with the same magnitude as a black hole like Sagittarius A. Or do we? First, what is gravity? Well, gravity is the weakest of the four fundamental forces, the other three being the strong force, weak force, and electromagnetic force. In fact, the strong force is 10 times stronger than gravity. 10 to the 38th power, that is. However, gravity is the only one of these forces that dominates at large distances and mass scales, such as solar systems or galaxies. Speaking of mass scales, the force of gravity is dependent on two main things: the mass of the two bodies and the distance between them. First, when looking at the equation, we see that mass is in the numerator, meaning that doubling one mass will double the force of gravity, therefore increasing the gravitational pull. Check out the simulation in Universe Sandbox that proves this theory. Here we have Earth 0.5 astronomical units away from the center of our star at another star, Sirius, a star with approximately twice the mass of our sun, and also the brightest star in our sky currently. We see how the Earth that orbits Sirius moves faster as the gravitational force is directly proportional to the mass of the objects in the system. And we know, using Newton's second law of motion, that when the force increases, so does the acceleration, making the speed increase as a result. But enough about Sirius, what about radius? More specifically, how does the distance between the centers of masses of the two objects affect the force of gravity? We can prove this again through Universe Sandbox, but instead of increasing the mass of the star, which happens to be our sun in this case, we'll instead increase the distance between the star and Earth. By putting one Earth-sized planet 0.05 astronomical units away and the other 0.1 AU away from the star, we see that the velocities again change, with the planet that's farther away from the sun having a slower speed due to a weaker gravitational force from the sun, leading to a lower acceleration, leading to a slower speed. So, what do these examples show us? Well, they tell us that the force of gravitation is directly proportional to the gravitational constant, the masses of the two objects in the system, and inversely proportional to the distance between the two objects' centers of masses squared. However, when thinking about how the small body will accelerate, the mass of it will be irrelevant, as it will cancel out when using Newton's second law of motion, as seen here. Instead of thinking about how gravity pulls us down, we can instead appreciate how it allows the moon to orbit the Earth and planets to orbit their stars. Or you could just see it as 0.000000000006674. And as always, thanks for watching.